I mean, positive integers by,
Was that?
why not just use the natural numbers at its time?
Because I'm being fancy. Ooh, fancy math, man.
So does it
Can't
include
say
0
n.
or not?
It does not.
Okay, cool.
And this is equivalent to, as Noah noted, naturals. Yeah. Sydney! Hi. Hi. Hey, friends. Hi. So when Labina came to talk to me last week, on Friday, I think we met.
Yeah.
I realized that I had given you a problem that we hadn't talked about how to do, and we really needed to talk about how to do. I forget which one this is, but there's one it's the second to last. It's like this, z to the 6th equals something, -9. And then the problem right after that, you also need this for, I think. But we'll talk about that. So and I'll take some questions, but let me see if this helps clear up any problems, and then we'll get into the specifics you might have. So the first thing is, a way to say this is find the nth roots of W. That's how I would state this problem. We're finding roots of a complex number. Like you have square roots and cube roots with real numbers. What is hidden underneath them is that there's these imaginary roots that are always there. So for example, if I had asked you to just find this, solve this, you can probably do that before this. I hope you can do that before this class. You would say x is 2. Turns out there's actually 2 other answers to this, but they're in the complex realm. So when we solve this problem, x cubed equals 8, there's 3 answers. When I solve this problem, z to the n equals something else, there are n different roots here. So there's n answers. That's the way to think of this. So in that problem that you're given, there's 6 different answers that you need to find. The good news is geometry makes this beautiful and simple. Is this true, Labina?
For C, I don't think so.
Labina?
I tried.
At least she's honest.
I know she is. We should ask her. My fault.
I have 6 answers. I do not know how to plot them.
Oh, well, that's a different matter. I'll show you all of that. I think we'll answer that as well. And then you'll be, yes, it's simple and beautiful. Tedious, perhaps, but simple and beautiful. So let's first start off. We've got this number W, sits out here, where our arbitrary complex numbers always sit, roughly there. And the first step is I'm going to convert this into its polar form. So we have the magnitude of W is that distance, and this angle here, which is not unique, is the argument. So if I convert W, so step 1 is to convert W into polar form. So W, let's just write it kind of in using notation and fancy language, is its modulus times e to the I, and then up here, argument of W. Any angle that describes that angle will work. So you could use, this looks like 45 or pi over 4, so I could use pi over 4. I could use -7 pi over 4 if I was feeling saucy. I could add 2 pi, I could add 2 pi's, I could subtract 2 pi, subtract 2 pi, whatever you want. Nobody's got that much energy. By the time you're into these exercises, you're not going to be like getting fancy with the angles, but you could. So let's assume that this is just for sake of notation, just this e to the I theta, r e to the I theta. Remember what this means. I'm going to write this out because I really want to drive this home. This e to the I theta is cosine of theta plus I sine of theta. This is a real number. This is a positive real number. This is a direction. So this here, this is e e to the I theta, and it's equal to the direction, and it's on the unit circle. It's just a point on the unit circle. So if I take the unit circle, well, I can't abide by that circle. It's a sad ass circle. Probably better to make the circle. Yeah. Like so. And if I swept out theta radians, and this is 1, I've said this before, but there's certain things that if you have them deep in your heart and mind, it'll make this whole class easier. E to the I theta is just right on there. As theta changes, you just spin around the circle. And so think of this as magnitude and direction. So let's go and make another assumption. Let's assume that z, the thing we're trying to find the nth power of, is also in polar form. So rho e to the I phi. I actually kind of notated backwards, but I'm not changing it now. I wish I'd put the r theta here, but whatever. So the problem becomes this problem over here. I'm going to call star. Problem star becomes rho e to the I theta, that's no rho, that's a p, that's a rho, e to the I phi to the nth power equals r e to the I theta. Here's w, here's z. Let's just do exponent stuff. That just multiplies, and this comes here, so it's rho to the n, e to the I n phi equals r e to the I theta. Is this okay so far? Yeah? Any troubles moving through here? All right, so remember now, in this polar form, this is the magnitude. This is the direction. So the magnitudes have to be the same. So immediately from this, we can conclude that rho to the n must equal r. And that's an easy one to solve, because this is just real numbers. And this exponent here and this exponent here have to describe the same angle. So it must mean that n phi is equal to theta, but that theta, remember I could spin around, so I'm going to put plus 2 pi k, so that this k is going to be an integer. And we're going to narrow that down in a bit. Let me stop. Let me know if you're cruising with this. It's Monday. No idea what your weekends are like. Eyebrow raises and things can communicate tons. So. All right. So this one here, this says that the magnitude is just the nth root of the magnitude of w. So this is easy. So rho is equal to r to the 1 over n. This says phi, I'm going to divide through by n, so the phi that we're looking for, right? We're trying to find that and that. Phi is equal to theta over n, the original argument divided by n, plus 2 pi k over n. We're almost done. So in other words, the z that solves this z is equal to rho to the 1 over n. R to the 1 over n, excuse me. R to the 1 over n times e to the I. Now this is phi. So we're going to have theta over n plus 2 pi k over n. And let me let you get caught up notationally, maybe mentally. And remembering that this k is an integer and it's going to go 0, 1, 2, 3, 4, 5. Notice that when k is 0, I'm at 2 pi times 0 is just right here. So when k is 0, it's right here. What does k have to get? So like then, if n is, say n is like 3 or something like that, then, shit, that's not a good way to explain it. Do you see that by the time k gets back to n, we've actually made it a full way around? So think of this. 2 pi over k, what is that going to look like? It's going to be 2 pi times 1 over n, 2 pi times 2 over n, 2 pi times 3 over n. So we're just stepping by multiples of 1 over n. Where should I stop k at? At n, right? Or n minus 1. So let's see, the first place we could do 2 pi times 0. That's right here. 2 pi times 1 over n, who knows where that's at? 2 pi times 2 over n, we're just stepping through by 2 pi's over n. And eventually we'll make our way back around. So we're going to go up to 2 pi times k times n minus 1 over n. Notice that there are n steps here. We start counting at 0. 0's straight out that way. 0's on the real axis. And then we make n equal steps around the circle. We're just doing that over and over again. So once we wrap around past this, we're just repeating things. So here's what we got. Let's take a look at that. What does this mean? And actually add this up here. K is going to go 0, 1, up through n minus 1. So what do we have as roots? We have our first root. So the first root, and I'm going to write this out, when k equals 0, we have our primitive root. That's called the primitive root. And that looks like this. R to the 1 over n, e to the I times theta over n. So it's the original theta just divided by n. So if I'm taking cube roots, that's theta over 3. If I'm taking fifth roots, that's theta over 5. Whatever that original theta was, we're going to divide it by the root power. And then the magnitude gets that same treatment. So the primitive root is going to be right, like say here. Here's theta over n. And then the length of this is r to the 1 over n. So it's the nth root of the magnitude and the argument divided by n. That's your primitive root. Then, let's take a look at the next one. When k equals 1, so we can see what this looks like. When k equals 1, now we're at r to the 1 over n. That never changes. We're always on a circle of radius r to the 1 over n. All these are going to fall on a circle of that radius. It's just where do they fall on that circle. So the next one is going to be e to the I theta over n plus 2 pi over n. So that is just an nth of the way around the circle. This is just the full revolution, 2 pi divided by n. So depending on what n is, it's going to look different. But here what I'm going to do is I'm going to add 2 pi over n and move to that next root on that same circle. And then I'm going to add 2 pi over n to get to the next root. So I keep adding 2 pi over n. Here's a root, here's a root, here's a root, here's a root, and then here's a root. And those are poorly spaced. This is a shitty looking pie. Somebody's got a big piece. You want all these pieces to be the same, but each one of these is just 2 pi over n around. And eventually you end up back at the original place. So let me summarize that while you're writing that up over here. I'm going to write a little sentence that might help. So the nth roots of a complex number are equally spaced around 0. I feel like if we have to do a real problem now, because this is the abstracted. Once you see how beautiful this is, it's gonna all fall into place. Because it really is a natural process. Bless you.
Bless
Thank you.
So let's do something. Let's find the cube roots. So solve z to the cube equals, let's come back to that problem that I had at the beginning. Z cubed equals 8, and figure out the cube roots of 8. We know there's 3 of them. One we've got, we can just do it in our head. Like, you don't even need to do complex analysis. Check this out. Let me show you how beautiful, and Labina, maybe this will help with the like intuitive understanding of what's going on. So all I need is 1. So z equals 2 is one of them, right? That's an easy one. And that's right here. So we go out 1, 2. There's the first root. I have 3 roots, and they have to be equally spaced. What is the angle between the roots? What, sorry, what was it?
130.
Yes, yeah, wait, did you say 130? 120, yes, thank you, yes, yeah, in radians.
Right.
So, look, 2 pi is full revolution.
Yeah.
How many?
3.
2 pi over 3.
Okay.
There you go. So yeah. But you do need to want to understand where that is. So if that helps converting that to 120, that's great. But what I think is, here's pi. You're going to get really good at this in this class. Pi is half a revolution. 2 pi is here. So let's see. So if this is a full pi, then I just back off a pi, which is 60 degrees, and I'm there. You might want to actually make a little circle of radius 2 first. All the roots have to be the same distance from 0. And now I'm going to step 2 pi over 3 this way and go to the circle. So that's 2 pi over 3. I just got to figure out what that is. Then that's trig town. Then move 2 pi over 3. Again, it'll be right here. And then move 2 pi over 3. And get back to where we started. So these are our 3 roots in the complex plane. And all we have to do is crank them out now. And to do that, you're going to want to think about the special triangles. Sometimes this is going to be impossible to do precisely. Try to avoid decimals at all accounts, because in a class like this, they're just not pretty. Don't like get your calculator out and get decimals and don't use that for pi, for crying out loud, please. Use pi. So let's find this first one here. So we got 2. This one here, let's do a little trig. Draw an angle down. All I need is this side and that side, and I know the complex number. And if you think about it, as soon as I know this one's going to be pretty easy because of the symmetry here. Right? This is pi over 3, and this is pi over 3. So what is this angle here? This pi over 3, and what is that in degrees? That is 60 degrees. So here's pi over 3, and that's 60. Here's a right triangle in theory. Here's, what's this angle? 30, which is how many rads?
5 or 6, sorry.
It's okay. Half this one, right? So half of pi over 3 is pi over 6. So yeah. This one's pi over 2, so definitely there's pi over 2. So let's see, this side is length, well, let's just do the special triangle. I always start with the shortest side, which is opposite the shortest angle, smallest angle, that's 1. Hypotenuse is 2, and then this side is square root of 3. And you can scale this however you want, except we don't need to here, because I know that this is 2. So this side here must be root 3, and this side here must have length 1, despite all appearances to the contrary. But that's not a positive 1, right? That's actually negative 1. So now I'm going to adjust for signs, so that's negative 1. Huzzah! I've got my second root. So my second root is going to be negative 1, the real part, plus square root of 3i. That's a second root. And what is the third root? Down here, what is this point? Using geometry and symmetry. So the real part, notice the real part didn't change. Yeah, -1 is still our real part, Lavina, does that make sense? Still -1 that way, yeah, you got the right numbers. So we got that. And those are the three roots. Oh, you don't believe me?
I might believe you.
No,
I'll buy it.
no, I don't know.
Oh, unfortunately.
We could check this out. I'm not going to do this. That sounds so boring. But I could check this out and prove to myself that that is indeed 8. It's just tedious. So look at how I used geometry and this equally spacedness of all roots. I went for super low hanging fruit to get one of them. Once I have one of them, I own all of them because they're equally spaced and the same distance. So I'd like you to practice this with me.
So,
Yes.
if it was c to the 4th instead of cube, we
That's right.
would have divided the circle into 4 equal parts and
Yes.
then did the triangles with those 4 angles.
Correct. So let's do that. Let's solve this problem. Z to the 4th equals, let's just go 16. Find all 4 roots, please. These are pretty ones. Not too bad. I'm going to do some weird stuff up here while you do that. As usual. The day goes by where you haven't done some weird stuff. Think about your life plan. Time to reevaluate. Yeah, can someone give us, what's low hanging fruit root?
2.
2. 2 to the 4th is 16. Woohoo, you just cracked the code. Bust that open.
Bust that open.
Bust that open. Pop that top.
Oh boy.
I was gonna say tap that keg, but I don't even drink beer. I had like
Me either.
one beer on Friday of the last day of classes. I was like, I'm gonna have a beer today.
Really?
I had a
How
beer.
did that go?
It was delicious. It was
Okay.
one beer's all I can handle anymore. I'm like, okay, now I'm tired.
Beers, that's interesting.
Now I remember why I don't drink beer.
Beers. No, my sister said beer tastes like garbage water.
Your sister is not. Well, it
I'm
depends on
gonna have
the
a beer
beer.
with your sister.
I drank a lot of beer, so I'm not gonna rip on
I'm a
beer.
tequila person myself.
It's also good.
I need to focus. Jesus.
Yeah, sorry, it's my fault. I'm bad.
Horrible together, Dr.
Terrible influence. What's that? So now you see, right, like how beautiful and you already got them cranked out. Yeah. Let me give you a different one. If you're done, do this just for good practice. This one will actually require a little triangle action,
Can
but
we do a Z6?
not no.
Yeah.
No?
Okay.
Let her live.
Okay.
Let her live.
Okay, let's do z to the 6th equals, now I gotta think.
Something weird.
I think it'll work out. I think it'll work out good. 180, yeah, it'll be fine. You'll be okay. Let's solve these. What a great day. Let me come around, help. Time for me to walk. How you doing? Music on, okay? Okay, where are you stuck? No, we're gonna do it here. So let's see, we're doing this one. What's one low hanging fruit? What's a 4 for you, 6? 2, I got 2, okay, so let's mark 2, so mark off 2 on the complex plane. Yeah, you can pick wherever you want. That's your 2, beautiful. Now, we have 4 roots. They are equally spaced. Yep. There you go. Yeah, got it. And they're each 2 away. So what is that? What is this one? Complex. No, you can just, like, it's just 2 up on the real imaginary axis, so you're thinking too deep. This one's 2. What is this point in the complex point? What number is that right there that you drew a dot on? What's the so we got complex one, we're using rectangle. Right, so here's like, here's 2, here's 2 high. There you go. Warm it up. Yeah, good job. What's that one? Solid. What's that last one?
What's the low hanging one?
I found out 4 roots.
Oh shit.
That's the game. Now let's look at this next problem. That one's gonna be a little trickier because there's no real number we can stick in.
Alright, chill out.
So convert negative 64 into polar form. That's your step 1. So take negative 64 and write it as pi e to the theta. Let's do that together actually. Let's drop it out. Okay. I'm sorry.
2. Cool.
Come back to me. We're here. It's safe. Everything's good here. Okay, so let's draw. So first step is convert negative 64. Let's write this over here. So 1. Write negative 64 in polar form. So step 1 to do that is draw it out. Where's it at on here? Okay, real axis. There's no imaginary part. It's on the real axis. Where's negative 64 on the real line? There you go. Yeah, perfect. Yeah, we don't want to tick off 64 of these things. You don't have enough paper. Convert that into polar form. What is the angle? What do I have to sweep to get that there? Yep. Just pi. You got it. You got it, friend. Cool. And how far out do you have to walk once you rotate pi degrees? How far out do you have to walk? 64. So it's 64 e to the pi I. Yeah. Now, when I want to find the primitive root, I take the 6th root of 64 and pi over 6. So I divide that angle by the root. I take the actual root of that number up front. So the most primitive root is 2 e to the pi over 6i. And that's just right there. And then then they're equally spaced around. So I'll give you some space so you can think and don't have me like breathing down your neck here. How's it going? How's it looking? Yeah, no, you tried to get, oh, it looks like you got it. But I'm missing one. It does take 2. It doesn't, it doesn't. Yeah. So I don't know that
I'm trying to make my
maybe
line
it's
straight.
just natural root.
That's what I'm trying to do.
I don't think so. How did you get negative 2? Because negative 2 to the 6 is a positive number, right? So that can't be our root.
I got there. I was just like,
That's
well, I was like, cause I was doing
Mhm, that's beautiful.
cause then, so I said, this is the negative
So these are
64
supposed to be
here. So then I was kind of doing some stuff.
Yeah,
So
yeah.
64 to the 62.
So- Yeah, and also divide that angle, cause your
Yeah,
notation, you
that's-
kind of screwed yourself up,
Yeah.
I
So you
think.
have two solutions, the ones on the y-axis.
There you go,
That's
there you go, there you go. Start from there, that's your
Yeah.
primitive root, 5 or 6. How we doing, no?
I think I got it.
Oh, they're beastly, aren't they? Okay.
Yeah,
Yeah,
I'll
that looks
underline
right.
the important things. That's what I do.
I think that looks good.
Okay.
Yeah, that's solid.
I should have just realized since it was even, if I had one, I could just take the negative. That's another one.
Exactly.
I did-
Yeah, that's okay. All these insights will come and you'll learn all sorts of
Now.
all sorts of tricks. Nathan, my friend, how's it going? They're looking good.
So you know that like maybe one plus square root of the other.
Yep. How did I come up with the actual points on there? Let's see, which one is this? That's a different file from here. So this is, so your sketch is a little off. Let's take a look at it. So these aren't the roots of 16.
Okay.
It's rotated a little too much, and so the first root, one of them is just equals 2, right? Is it okay if I draw it there? So it's equals 2 is right here.
Okay.
The rest of the roots are equally spaced around, so you got that idea, but this anchor of 2 is essential. Now I go, here's the next one, here's the next one, and here's the next one. And they're all 2 units away, so what's this guy gonna be? What's this guy gonna be? What's this guy? Does that make sense?
Yeah.
Yeah. And then, so that's how you do that, so this one's gonna be, this is gonna be 2i, negative 2, negative 2i.
Okay.
Yeah, does that make sense? Beautiful. So then down here, step
I also
one.
did that one wrong, but yeah.
it looks better. It definitely looks better. Like these look appropriate. They're not like there's no detail here, so it's hard to tell. But like the picture looks right.
Okay. Yeah, negative 64. Start there and then
Yeah. So everybody on the yes sir.
yeah, no, I got
Oh,
it.
you got it. You got it. Cool. So how's it going, my friend? What do we got here? Oh, you're doing the beast.
Triangles.
So where's your negative 64? Where is that in polar form on here? I'm just curious.
It's not there.
It's not there. You kind of did. Okay.
It's not.
It's not. So like, how did you? So this actually looks right. I have no idea how you got these things, but this,
Skipped a few things.
yeah,
Middle.
yeah. But the spacing here looks a little weird, right? Because this looks like you divided it into either 8ths or 4ths. There should be 6 lines, and
1, 2, 3, 4, 5, 6.
wait,
2
what?
of them must be the
1, 2,
axes.
3, 4, 5, 6.
I don't think an axis involved. Oh wait, imaginary axis maybe.
No, 2
Let's
of
take a
them
look.
are on
Let's
the
take-
real axis.
It can't be.
2 are negative 2.
Neither of, if 2 to the 6th is positive 64, negative 2 to the 6th is also positive 64.
Oh my gosh, you're right.
I hope so. It's gonna be a bad freaking semester. And if I, yeah. Let's talk here. Let's check in.
Yes, please.
Yeah. So step 1 is convert negative 64 into polar form. So draw a picture. Never do this without a picture. You're gonna hurt yourself. And I've seen some people injure themselves already this morning.
Yeah.
So negative 64, that's pi, and the radius is 64 units, right? You always talk about the positive distance going out. So this is 64 e to the pi I. Pi I pi. So, the most primitive root is easy to get. Once I've got this, step 2 is find the primitive root. And the primitive root is just going to be 64 to the 1/6. This is like computer science numbers, right? No, and then e to the what angle? Where's my
6i.
pi over 6i? You just take the angle divided by the root depth you're seeking. So that, right there, if I wrote that, I got partial credit. I may not know what the hell that means, but it's partial credit. Now I gotta show I know what it means. So this is 2e to the pi over 6i. So I'm gonna draw that out. What is this in degrees, pi over 6? 30. We're gonna be so freaking good at that by the end. So let me just put something soothing up here for you. 30 degrees.
Yay.
Yay!
I understand.
Pi over 6. I'm gonna write it real tiny. It's pi over 6, but it's 30 degrees. And I move out 2 units. So this is length 2, right here. And so this number is the primitive root. Let me stop. I don't want to go further until we're positive that makes sense.
That makes so much sense.
Does that make sense? Yeah. So, like, please do it this way. There are other ways to do it, but until you've mastered this way, don't try a different route. The picture helps the brain. So, I have 6 roots, and I'm going to equally space them. So how far apart will they be?
Pi over 6.
Pi over 6. Wait.
Or pi over 3.
Yeah. So 6 roots. Take the full revolution, 2 pi. So that's pi over 3 apart. So the roots are.
Oh,
You see where I'm going with that, Sydney?
okay.
Pi over 3 apart. And how many degrees is that? 60. Beautiful. That's 60 degrees. That's equivalent to 60 degrees. Your brain works with 60 degrees. Practice using radians, but this is pi over 6. So this is 30 degrees. If I add 60 degrees to that, where do I end up?
90.
Fuck yeah. Right there. So look, I'm just stepping by 60 degrees there. What is that number?
2i.
2i. Beautiful. Where is the next root? Now I move another 60. How short, so this is 60, that's a sad ass arc, but somewhat, this is a depressed arc. That's better. What is this reference angle right here that's left? What is this angle made with the horizontal axis? 30,
Pi over 6.
right? Does that make sense?
Yes.
Yeah. So, and I'm out here, and so all I gotta do is trig this thing. This is a hypotenuse of 2. Oh my fucking, oh sorry, but oh my freaking
Oh my lord.
Oh
kohlrabi.
my goodness on my soul.
Oh my goodness on my soul.
There goes all this down the hole.
Triangle.
Yeah.
I scaled it so you wouldn't have to scale it from this. Like, that's why I made this too. So that like you can just plunk that picture and you go, oh, that's negative square root of 3 plus I. This is square root of 3, distance, this is 1.
Yeah.
Step another 60, that takes you under by 30.
Negative square root of 3 is
Negative square root of 3 minus I. Hey, here's a little tip. If a complex number is the root, so is its conjugate.
G.
So let me kind of put that up here for you. Here's a little sanity check. If z is a root, so is its conjugate.
Would that
Go ahead, Noah, sorry.
would that not only work for even roots?
It would work for all. It's gonna work for all. It'll work for all. So with that in mind, I'm done. Right, I've got 3 on the top, therefore I have 3 on the bottom, all the conjugates. Here, that's the conjugate. What's the conjugate of 2i? Negative 2i, beautiful. There's the second, whatever, root. And then what's the conjugate of this jump here? Let's see, this is square root of 3 plus I. What's its conjugate? Square root of 3 minus I.
I understand.
address Noah's point. But I want to make sure that this sounds right. These are the roots you got, right? Definitely, Noah?
Yes. No, but yeah, it worked right. It worked when you did 8s to the 3, and I was an odd that.
It should work with any.
It makes sense if it's a root of a real number, for sure.
For sure, because then it doesn't move, right?
Yeah, because then it's like one of them is on this and all the others are reflected across
Yeah.
that.
You know what to do now?
Yeah, I'm still going to do all the homework problems, but it's still at the negative. I totally blew off the theta over n. So
That's what I thought. Yeah. So check it out. Now, I want to point out something. People are always shocked to know that there is a fundamental theorem of algebra. And not like abstract algebra, like the algebra you learn in like junior high and stuff like that. The fundamental theorem of algebra is that any polynomial, so this is a polynomial, an nth degree polynomial has n distinct roots.
I knew that.
yeah.
Yeah, good. Did you know it was the fundamental theorem of algebra? Now you do. That's the part people don't know. You know that fact, but you don't know it's FTA. Whoa, damn. So, once I have the roots, I have the factorization as well. That each root corresponds to a factor. So if I said to you, take this problem, rewrite it like this, here's a 4th degree polynomial in Z. You can factor it by just writing Z minus a root. Each factor is Z minus a root. So there's the factorization, the complete factorization. Over here, I'm not going to write this out, because this will be pretty atrocious, but it'll look something like this. Z to the 4th, Z to the 6th, plus 64 is equal to Z minus 2i, Z minus negative 2i, which is the plus 2i. Z minus then this other shit, right? So forth and et cetera down the line. Put 6 factors, and you've got it factored. Look at power. Does this help with that problem? Hell yes. All right. Let me address the very last problem, because I think that looks something like this.
For 11C, it's like 9 to the 1/6, so that's kind of an ugly number.
Ooh, can I see? I'm sorry. Which problem, Libina?
11C.
11C. Here, let me just look it up. I'm sorry.
Aw, jeez.
Complete. Everything must be complete. What folks say? 11C. Yes. So Z to the 6th equals negative. That actually should be just like this problem. 11C, because you have Z to the 6th equals negative 9. It won't be pretty because the 6th, so your magnitude will be square root of 3. No. Wait. Hold on.
Cube root of 3.
What is the 6th root?
root of 3.
Yeah, what is the 6th root of 9? Right?
Cube root of 3.
3, yeah,
So,
cube
yeah.
root of 3.
Cube root of 3. So this will be your magnitude.
Yeah.
Oh, that's kind of.
Just case, just notation. Pretend it's 2. It'll be okay.
It's fancy too.
It's a very fancy 2. Yeah, so approximately 2. Everything will be approximately 2 as you look back at these examples. So the very last problem gives you something like this, exactly precisely like this.
Oh.
Solve for Z. So this is more than a root. Suggestions? I know Labina knows because we talked about it. Does anybody have any suggestions on like a first stab here?
Let ka equals a cube.
Ooh.
Yeah, I'm doing Japanese letters.
Why?
Oh, okay. I'm gonna pick a C because that's the closest I know to what you said there. So, what was the letter you used?
Katakana.
Can you make it?
Yeah, I can make it.
Stomach.
Cool.
Gorgeous. Nice.
Beautiful.
Oh, that's
I like that one.
Japanese letter.
Yeah, that's use Greek letters and they get annoying after a certain point.
True.
And I need to keep up my strategy somehow.
That's good. I love it. I freaking love it. So make a substitution, and this is actually a quadratic equation in ka,
Yeah.
sure, in z cubed. Because you can write it like this. It's z cubed squared minus z cubed minus 2. And so you make the substitution.
The little thing at the top is not supposed to be there. Yeah.
Well,
Yeah,
I mean, I'm just going by what my teacher taught me.
We weren't gonna ask questions now, I promise you.
I'm gonna make my version of it, which may or may not be accurate, but hey, I'll try. So solve for this variable here using the quadratic formula. So ka equals the opposite of b. Let's just say 1/2. Put the 1/2 out in front. Opposite of b, so 1 plus or minus square root of b squared minus 4 times a times c, so that's plus 8. And so check this out. You've got some work to do here. Let's keep the original due date, but know that, you know, if you need a little more time, just let me know. So this is going to be 1/2 of 1 plus or minus 3. So what is that? That's -1 or 2? Yeah, so what you actually then have to do is find, and this will be easy now. You need to still find, so this is just ka, which is z cubed. So z cubed equals 1, solve that, or z cubed equals 2, solve that. Find the cube root of -1, find the cube root of 2.
That's a lot better then.
Isn't it? And you might even be able to picture this in your brain now.
Yeah.
Practice picturing these things in your brain, and it's just like, it'll be cake on paper.
It's just the negatives that trigger me off.
Yeah.
Stupid.
What?
I didn't say anything.
I didn't think so.
Awkward.
No.
I'm ready for you, Sydney. I'm here. I'm just ready for ping pong.
Watch yourself, Dr. King.
Yeah, I'll watch it. All right, any questions here? We can get our homework done, I believe.
It's possible.
Yeah, okay. Here's some more stuff now. I'm gonna give you more things. Let's start talking. I sent out like an email or something, right? Like, please read through some definitions, because I don't want to freaking read them to you. Good. Let's talk about that stuff. Let's just kind of go through. And I guess first off, do you have any, as you were reading it, is there something that was confusing? There we go. Is there anything that was confusing in that discussion?
I think like differentiating between the interior boundary accumulation and isolated point.
Yeah, I don't get accumulation really.
Cool, awesome, let's talk, great. Yeah, especially accumulation is very subtle, very tricky thing. All right. So this is all called topology. Boy, if you go to grad school in math, take a topology class, because it's just beautiful and cool, and all you'll study is weird stuff that's just weird. Every day, something weirder. It keeps getting weirder, and that's why we're here. Unless you're here for applied math, and then you still need to be ready for weirdness. You're in the wrong profession if you don't like weird stuff. So let's just take a look. Let's go through the definitions really quick. First off, I want to touch base on a few things here. There was a definition that if I had two complex numbers, then z minus w, the modulus of z minus w, we define as the distance, or we can think of it as the distance between w and z. So, I mean, you notation, and you wouldn't be doing anything weird at all. It just gives the distance between two complex numbers, like the literal magnitude of that length between the two. So with that in mind, what is this? What set is described here? So the first set I want to talk about is, let's fix A. So this is a fixed number. What is this set here? And then also R is a positive number. When you write R as a positive number, that immediately says it is a real number. I just thought of talking about that. So this is the set of all Z and C, such that that is true. What does that look like? Think of the interpretation of modulus of Z minus A as distance. What are we describing here? Picture. It's fun. It's good. Tea time. Let me help translate. Yeah, got it?
No, but,
See if this helps. Just see if this verifies what you're thinking. It's all the Z and C, so it's the distance from Z to this point A is
yeah,
R.
that's what I was thinking.
Yeah, what are you thinking then?
So what is, everything is, like, all the distance is greater than R, greater than 0?
Equal to R.
So everything is greater than 0, like all the distance.
Yes, R is a positive number for sure.
Yeah.
So here's A. What does the set look like relative to that A?
Is it like a circle?
It is precisely a circle.
Oh, I love
Okay.
circles.
It's all the points equidistant from A. In fact, R units from A.
Yeah.
So it's just a circle of radius R, center A.
Beautiful.
Yeah, not bad, right? So this equals circle, rad R, center equals A. Cool. What is this set?
Everything out of, like, except the circumference, like everything inside.
At the inside. So like the stuff inside without the edge. So this is, and I'm actually just going to use this word because it's precise, and we're going to talk about it, but it's the interior of a circle of radius R centered at A. So it looks like this. And here's how you would draw this. I would put A, and I would, figure out roughly whatever R is. Put dotted lines around it R, and then you can kind of shade in inside there. Whatever it takes to indicate that. Just the stuff inside. Cool. We will need those beasts. So let's talk about those definitions that were troubling. First one was some definitions. We have a subset of the complex plane. So when you do that, just draw some kind of weird blob. And that's your G, whatever. And it looks like it has a solid boundary and it's not fuzzy, but that just doesn't have to be the case. If I wanted to indicate that, I would take off that little dot. I would make that spotty. So we're going to say that A is an element of the interior of G. So I'm going to write that out. So A is in the interior, and I'm introducing some notation that wasn't in our book, interior of G. That's how I read that. Here's another way to write that. you'll see this in other books. A is an element of G with a little circle above it like that. That just means the interior of G. That happens if we can find an open circle, an open disk around A that is also in G. So what do I mean by that? Well, let's take a look at this picture here. So let's take a look at the set of all Z such that Z minus 1, how about 1 plus I? So Z minus quantity 1 plus I is less than or equal to 1. Before I even go, could you sketch that for me, please? What does that set look like? This is a good little call of the wild moment for me. I'll be right back.
I was wondering when you were gonna go.
Yeah, I know, it's been a while, right? Excuse me.
Basically same. Do you think I understand anything written down on this piece of paper? Not a damn thing. Not a damn thing. I've heard it. It's been a minute. It's been a minute.
Probably when I was like 2.
I mean, I can think.
Yeah, we're just a little
It's
bit.
fine.
I'll probably sit on that side because I'm even starting to lot with this door open.
What is that in words? Oh, should I have peed longer?
Is it a circle over here? It's one.
Yeah.
And it's interior.
And it's stuff inside, right? It's like a disk, like a closed disk of radius 1. Where's the center?
1 plus I.
Beautiful. Here's 1. Here's I. Here's my center. Radius of 1 means I'm going to be tangential to those wow.
Draw
I
the
hate-
circle first,
Yeah, I should have done, yes, correct.
but I didn't do it either.
I know. Circle first, center, there's 1 plus I. Yeah, there's 1.
Oh, so they touch.
Yes,
Okay.
because 1 unit, right? So it's just 1 unit straight down and 1 unit straight across where the center is. And so it's all this stuff here, including the boundary. So this is a closed disk of radius 1 centered at 1 plus I. So let's take a point. Let's look at some points here. See this definition about interior. I'm in the interior of a set if I can find, if there exists, there is just 1. I don't need a bunch, I just need freaking 1. If I can take me, here's my point, am I in the interior? Sure. Here's a nice disk around me that's also in the set. That is contained, does this make sense here? That whole disk is in the set, right there. What if I get super close to the edge? Is that in the interior?
I think so.
Yeah. What kind of circle am I gonna have?
Very
A
small.
small one.
Tiny, a wee tiny circle, but I can get one in there. Yep, that's in the interior. What about this point?
No.
There's no circle around that point that is contained in the set itself. So this is interior. This is interior. This is not interior. Because there's no circle around this thing that is completely contained inside the set. There's always a little spillage outside, and there's stuff inside, but there's always spillage out of the set, no matter how tiny, no matter how freaking tiny the circle is, part of it's always outside. So that's not an interior point. That's called a boundary point. So a boundary point, so let me just kind of flow into it, I guess that's what I do. A boundary point, every disk around that point touches inside and outside. So this is a boundary point.
See, if the book said touches inside and outside, I totally would have understood the first time.
I mean, I gotta get paid for some.
Right. No, that's fair.
Yeah, right. A boundary point, because every disk centered there spills out and in. It touches inside stuff and outside stuff. That's a boundary point. Okay, let's see, I lost my page because my book exploded or something earlier. So, back to that definition. Oh boy, this book is compact. Book is very compact. So, oh wow, hey, I'm like flowing through here. Accumulation point, let's do that one. This is what I think was troubling you. And I really, honestly, I appreciate that it troubled you because that means you looked at it. And that's great. It really means a lot. So an accumulation point. Let's look at their definition and then let's turn it into English. Or intuitive things. So a point, C, is an accumulation point of G if every open disk contains a point of G different from C. So, accumulation point, I'm going to give you this a nice way. Every punctured open disk. What is a punctured open disk? It doesn't have a center. It takes out the point at the center. So, a punctured open disk is just a disk with the center removed. So what do I mean by that? Well, it would look like this. It would be the set of all points in Z, in the complex plane, such that this distance here can't be 0. We can't get to the center of the thing and then less than R. This could be less than or equal to. If you wanted to add the boundary in, you'd put equal. If you wanted open, you leave it like that. But what this does is it removes the center. It removes the possibility that Z equals A. So punctured disks look like this. Here's A. I do like a little open circle. I'm gonna kind of put it like that, and that's A right there. So it's everything in that disk except the center. This is a way better way to think about accumulation. So every punctured disk, let's see here, C is an accumulation point if every punctured open disk centered at C intersects the set. Accumulation point of G, sorry, set G, there we go. That's a lot of hacking there, sorry about that. So, let's take a look at some accumulation points. Let me give you a nice set. So let's just look at this simple set here. I want to do a weird one to start with. So it's the set of all Z equal to 1 over N, where N equals 1, 2, 3, like so. This is all real. This is all this could be real analysis. right here. So we draw this out. Really just all happening here in the real axis. Let's see, when n equals 1, we have z equals 1. When n equals 2, I have a half. And then I've got a third, and then I've got a quarter, and then a fifth. And I see this infinite regression of points headed towards 0. Is 0 in this set?
No.
0 is not in this set, right? Because this, we don't solve that. So there's no n that's going to give you 0. But we do get as close to 0 as you'd like. Tell me how close you want to zero, how close you want to be to 0. I'll just pick a super large n, and that'll get you in there. So let's ask some questions here now. Where are the accumulation points? Well, I'm going to tell you this first one. So 0 is the only accumulation point. If this is G of G. Because if I take 0, so let's like zoom in here. So here's 0. Let's take a punctured disk around there. So that's a punctured disk. And think about what this set is doing. It's a bunch of points that are getting closer and closer together and shrinking towards 0, right? They're just kind of like getting closer and closer. No matter how big or small this disk is, eventually there's going to be a 1 over n inside there. No matter what you pick this radius r to be, all I have to do is pick n to be big enough so that 1 over n is less than r. 0 is not included, but every punctured disk around 0 has this property that, let me write that sentence out. So every punctured disk centered at 0 contains points from G. And that fits the definition of an accumulation point. Let's prove to ourselves that there are no others. But let me stop for a second and let you absorb that, because that's important to understand. And this will be it. We'll just call it after today. We'll call it after this. Pick it back up on Wednesday. So what about 1? Why is 1 not an accumulation point?
Because the disk is punctured. And if you want to do like a 1/3 radius.
Yeah. There's one right there, right? That disk, and Noah like picked even a specific radius for us. He said, if I take a disk centered at 1, I can't count that point as being an intersection with the set. You can't take the point that's accumulating things to be the point in the set. So is there any, can I find a disk around 1 that doesn't intersect any of this stuff? And Noah said, yeah, just go out a third, because this whole distance here is a half.
Okay.
If I can find one disk around that point that doesn't touch the set, it is not an accumulation point. One important thing to notice is an accumulation point doesn't have to be in the original set either. Right? This set had an accumulation point that was 0. 0 is not in that set. So just keep a note here that accumulation points, I'll just put this up here, don't have to be in the set. And quite often they're not. In fact, what if we took this set right here? So consider G equals set of all Z less than 1. What does that look like?
Interior of the unit circle.
Interior of the unit circle. Z equals 1, modulus of Z equals 1 is the boundary of that set, but we're just looking at the inside, so it's just going to be this creature here. Is this an accumulation point? So is there some disk around this point that doesn't touch the circle elsewhere? Because so like, look, we got all the inside stuff too. Maybe that. Is that an accumulation point? Take it out, draw a disk around it. Does that disk intersect the set? Yes. That is an accumulation point because everything that's here, inside here, is an accumulation point. Just draw a little disk around it, and all that stuff is in the set. Is the boundary, here's a point on the boundary, is that an accumulation point?
Yes.
Draw disks around it. Can you find a disk that doesn't intersect the set somewhere else? That doesn't.
That doesn't intersect the.
Can you find a disk around this dot here that doesn't somehow touch stuff in the set? You can't. So this is an accumulation point. If you can find a disk around your point that doesn't touch the rest of the set, that's called an isolated point. So an isolated point has space between it and other stuff in the set. It makes sense, it's isolated, it's not close to anybody. Accumulation means there's a fine mist building up toward that point. It's like we're almost there. We're accumulating at that location. And it's okay, we are gonna practice using these throughout the semester. We're gonna come in on Wednesday and practice. And there's no homework with this and no stress, right? Just do roots. Roots. So I would love to collect that at the beginning of class on Monday, Wednesday, and if you need more time, then talk to me. We'll talk. We do not meet next Monday. No one meets next Monday. Yes! Long weekend. Yes! It used to be like the second Monday of the semester, and that was always ridiculous, right? It's like, I don't need a break yet. Well, if it's going to be a break, then I just shouldn't have started the semester.
No, absolutely.
Right? Thank you, friends.